Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be talking about buffer capacity, which is really another way of talking about how many protons or hydroxide ions can I throw at a solution before I make its pH go all sorts of whack. So in order to understand buffer capacity, we first have to understand what a buffer really is. And at its heart, a buffer is a ratio of a weak acid and a weak base. And they can absorb changes to the pH by turning them into changes in this ratio. So, for example, if I have a weak base like acetate and I add a strong acid, all those extra protons quickly nom onto the acetate and turn into acetic acid. And so the pH will go a little bit down as I have a slightly more acid in the system. However, conversely, if I have a whole bunch of hydroxide, which should send the pH shooting straight up, instead they'll go ahead and attack the acetic acid and turn it into acetate. And then the pH will go up only slightly as I just change this ratio. And so what we're really doing here is modulating the changes in pH as we're still going to retain some weak acid and base in the system. So as long as I have both a weak acid and a weak base, any pH changes we have will be fairly minimal and stay pretty close to the pH. Now, the question is, when will a buffer have the most resistance to an external pH change? Well, it's going to be when this log term is fairly small. And this is going to is typically considered to occur when that ratio of acid to base is somewhere between 1 to 10 and 10 to 1. Now, the reason why we tend to use these numbers is that, first of all, logs being the way they do go on powers. So if I have a 10 to 1 concentration, this will be a log of 10 plus 1. If I have a log of 1 to 10, this would be 0.1 or a log of 0.1 or minus 1. So this will keep the pH somewhere in between plus or minus 1. And as soon as you get outside of that range, the concentration ratio will change a lot more rapidly with the actual values, and the pH quickly starts going out of control. So in this range, however, any sort of pH change will be fairly modulated. So let's go ahead and say I have a 1 liter solution that has about 1 mole of acetic acid and acetate combined. So this would be an acetic acid buffer or an acetate buffer is how it's typically referred to as. Now, the concentrations of the individual components would be somewhere between about 0.9 molar acetic acid and about 0.1 molar acetate. On the low end, so this would give us a pH of about 3.75. And on the high end, this would be a ratio of about 0.1 acetic acid and 0.9 acetate. So again, being richer in acetate, the pH will be higher, about 5.75. With again the most controlled pH near that middle point of 4.75. So this is really our buffer region. So what would it take to at what condition will I have the most stable buffer? Well, a good place to start would be right in the middle, where you have about even amounts of acetic acid and sodium acetate. So if I have a 1 liter buffer of equal concentrations, the pH will be the pKa at 4.75. And in order to break this buffer, or essentially to bring it out of balance or out of that buffer region, I'd have to add a little bit more than either 0.4 moles of HCl to essentially make it uber acidic and bring the pH down below 3.75, or a little bit more than 0.4 moles of NaOH to bring the pH up to about 5.75, after which, if I add much more of either HCl or NaOH, the pH will quickly change in either direction. And we'll talk more about that next time. However, what would end up happening if those concentrations were slightly off kilter? So what would happen if, say, if the solution was instead 0.8 molar in acetic acid? Well, at this point, we can plug in our values into Henderson-Hasselbalch and find out that we'd have a pH of about 4.15. So again, slightly more acidic. But at this point, it'd only take me about an extra mole of HCl to essentially make the system so acidic it's no longer buffering. On the other end, it would take us a lot more moles of sodium hydroxide to essentially break the buffer the other way and make it more basic. So in general, the common wisdom is that if you want the strongest buffer, it's going and resistant to the most types of changes, you're going to have a fairly even concentration of that weak acid and weak base. That way it can resist changes in either direction and have what's said to be a higher buffer capacity, as it's less likely to break or not become a non-buffered solution. However, that said, if you know that you're more likely to experience changes from one direction than another, for example, if you know that you're more likely to be exposed to base than acid, having a system that's richer in the conjugate acid could be a good idea. The other method you can essentially break a buffer or change its capacity is by changing the overall concentration of the buffer. So previously we had 1 molar buffer solution, which is pretty strong. What would happen if I made that buffer a little bit less concentrated? So what would happen if I had again, that 1 liter, but now instead of a 0.1 overall concentration or a 1 molar overall concentration, I have a 0.1 molar concentration. Well, logically in this case, it will only take me about a tenth of as much HCl to bring that ratio all the way up to acidic, or a tenth as much sodium hydroxide, 0.04 moles now, to bring it all the way to the basic range. So it takes overall less acid or base to quote unquote break the buffer. So this is one of those important things. So if I want to have the best buffer I can, really what we're going to want to have is those weak acid, conjugate base pair to essentially have both very large concentrations, so I can absorb as much HCl or much NaOH as possible, and to keep those concentrations fairly equal so I can resist both changes equally. So next time, we're going to be looking a lot more in detail at how the pH will change as I start mixing acid and bases as we start talking about titrations. Until then, take care.